I sincerely hope you recovered from the end of the last mini lecture with that really nerdy joke. So now, if you're recovered, we will dive off into the whole idea of protecting groups, which is the subject of mini lecture 3. And there is my protection? Yeah, well, whatever. Okay, so we're scooting along in all these kind of random topics that are associated with making new molecules. And certainly one of the big problems associated with making new molecules is the issue of control and selectivity. So that's what this section is all about. Basically, when I have multifunctional compounds, how do I control the darn reagent and tell it, I want you to react here and not over there? Well, we've seen a lot of examples of this already, believe it or not. So, say, for example, we have this cyclopentanone. We can carefully control by judicious choice of reagents and conditions whether we make the kinetic enolate or the thermodynamic enolate. So this was actually introduced in section 10.3. This is our kinetic enolate, and this is the thermodynamic. Thermodynamic meaning more stable because it's a more highly substituted enolate. The kinetic was the kinetic enolate because it was easier to deprotonate by removal of one of these hydrogens, one of these alpha hydrogens, because it's more easily accessible, therefore it's faster. So we can really accentuate that by keeping the temperature down and using a really bulky base like lithium diisopropyl amide. Whereas we could use tert butoxide and just room temperature or above to allow the whole shoot and match to equilibrate. Kinetic ones form first, but it can, if we use potassium tert butoxide, we can allow it to equilibrate to the thermodynamic, which is more stable. So another example of selectivity is seen in this example. So for this alkyl halide, say we want to make an alkene. Well, we know if we choose the right reagents and conditions, we can either make the more substituted, more stable thermodynamic product here, more stable because it's a more highly substituted alkene, or the less stable, less substituted alkene. This can be achieved by using the Hofmann elimination, or a really super bulky base, whereas we would get this one almost exclusively, definitely a major product, by using, say, CH3, CH2O minus sodium ethoxide in ethanol. And of course, to favor elimination as opposed to substitution, we'd use heat. So we can use concepts like the sterics of the reagent, a bulky LDA to remove the alpha hydrogens that lead to the kinetic enolate, or a really super bulky base to give us the less substituted alkene. And we can take advantage of reversibility and irreversibility, as we just saw in 1.2 versus 1.4 in the previous chapters. All of these things allow us to direct the outcome in the direction we want it to. However, back to this little problem. I want this carbonyl to be reduced. How can I get that carbonyl to be reduced when it is the less reactive site? No matter how bulky my reagent or how warm or cold my temperature is, this thiol is going to go for the aldehyde. So this calls for some other strategy, and that other strategy is the use of protecting groups. So a protecting group is a temporary mask for a reactive functional group. Key to having a good functional group is that it's easy to put on your molecule and easy to take off your molecule. You don't want to use up a lot of time, and you sure don't want to use up a lot of material doing this. You want to have a nice high, ideally quantitative yield in both the protection and deprotection stages. So by protection, I mean you take your starting material and you add something like this blue dot, whatever that is, that completely hides my reactive aldehyde from future reactions. And it only stands to reason that the blue dot's going to go here because, after all, this is the more reactive site. So there's no problem getting the protecting group on. Then, with the protecting group masking my aldehyde, I can go ahead and carry out my reaction. The thiol now is forced to react with the less reactive ketone because there's no other choice. It doesn't even know there's an aldehyde there because it's not. The thiol ketal is formed. I can then add my Raney nickel, get my reduced product, and now all I have to do is deprotect, remove that temporary mask to get my final product. So that's the strategy behind a use of a protecting group. You can see the obvious problem with it is that we have 2 additional steps, so it means a longer synthesis and overall a reduced yield. So we'll look at just a couple of functional groups in terms of what kinds of things we use for protecting groups. And the first one is aldehydes and ketones. The reason we are using that is because we just learned about that. It's a good reinforcement for the formation of acetals and ketals. Alright, so let's say I would like to carry out this transformation. We haven't seen ester chemistry yet, but you can certainly imagine that this is a delta positive because of the dipole here, just as a ketone is a delta positive. So I have 2 electrophilic centers right here and right here. And clearly, you can imagine that that oxygen could be pushing electron density into the ester group. So, yikes, this guy is more reactive than the ester, but as you can see, I want the reaction to take place at the ester, not here. So I got to mask this guy somehow or other, and that is accomplished by carrying out the ketal formation chemistry that we learned in the previous chapters. So protonation first, we're under acidic conditions, makes this more electrophilic. It's more reactive in the first place. Then treatment with this diol gives me the cyclic ketal. And ketals are stable to base. You may remember that for me to carry out the reverse reaction, I have to add lots of water and acid necessary to protonate the oxygen of the ketal. So now I've masked my ketone as a ketal. I can treat it with my reducing agent. We'll see later on that lithium aluminum hydride reduces just about any kind of carbonyl, including esters, takes it all the way down to the alcohol. There's a question for you. What's the oxidation state here? What's the oxidation state here? That way you can figure out that this is a reduction and it needs a reducing agent like lithium aluminum hydride. I should point out that this means mild aqueous workup. So you may destroy some of your ketal, but when we really want to go back to deprotect the ketal completely to get back to the ketone, I wonder what those reagents are. So there's two problems for you buried on this one. Figure out change in oxidation states and what are the reagents I need to go from here to here in the deprotection stage. Deprotection. Alright, so protecting group for aldehydes and ketones, you make a ketal, and cyclic is better than acyclic because it is actually easier to form because of that intramolecular nature. Alright, another functional group that is very often needed to be protected is an alcohol, because an alcohol, of course, has an acidic hydrogen. It's not a very acidic hydrogen, but if you had a Grignard or organolithium around, you'd have problems. So protecting groups for alcohols are many. Here's an example. This is basically an analog of cholesterol. Let's say I want to synthesize this cholesterol analog. Well, I see that it's got two alcohols, and knowing my alcohol disconnection, I know it would be easy to push those electrons back in and imagine breaking this down into this nucleophile and this electrophile. Minor problem here though. If I'm going to make this a nucleophile, that means I'm going to make it into a Grignard, and so I would need the bromine here so that I could add magnesium to it to make the Grignard, to get here, to add this guy to this guy, to make this new bond, yada yada yada. But I got a big problem with the Grignard formation, and that's this acidic hydrogen. As we've already seen, you can't make a Grignard reagent in the presence of functionality that has an acidic hydrogen. So this calls for a protecting group. So I start with my desired starting material, right? And then I need something to protect it, and this is what I'll do. I'll make an ether. And this is not any normal ether. This is what is known as a silyl ether. So we know my alcohol is the nucleophile, and we're certainly familiar enough with leaving groups and polarity to realize that with this chlorine on here, that's bound to be a leaving group with a polar silicon chlorine bond. So I should be able to take my nucleophile and react it with that electrophile and kick out that leaving group in a perfectly normal substitution reaction to get, and we'll just ignore the rest of the molecule here, this product. So you should notice that the hydrogen did not fly off. It's still sitting there. I've kicked out Cl minus, and now basically anything you see protonated, you need to deprotonate it, and that is why pyridine is present here. That's what this guy is. So the pyridine deprotonates to give the protonated pyridine, which has a counter ion of the chloride. So what do we got here? We have made a silyl ether by putting this group on your oxygen. Two things to point out. First off, this is a pretty strong bond. Silicon's a little bigger. This is a very easy reaction to do, and it gives very good yields. Another thing to point out is that there's a lot of variety, a lot of variability in the alkyl groups that are on the silicon. I think your book has the dimethyltert-butyl, there's diphenyltert-butyl, there's triphenyl, you name it. There's all kinds of different silo-protecting groups, and they all are put onto the alcohol in the same way, but have different levels of robustness. In any case, now that my alcohol is protected, I have no acidic hydrogen anymore. Now I can carry out my Grignard. So I form my Grignard reagent by adding magnesium metal to the bromide. Then I can add my aldehyde. Addition of my Grignard, of course, goes way the heck over here. Woo! I make my new carbon-carbon bond and then work it up, protonating the alcohol. I want to point out that this is a stereocenter, and so I've shown this as a squiggly line because right now I don't really have any control over the stereochemistry here. This would end up with a pair of epimers, because if the hydroxy is up or the hydroxy is down, those aren't enantiomers at all. Those would be diastereomers. So I'll end up with a pair of diastereomers where the two stereocenters here are referred to as epimers. In any case, this was my protection stage. Now I have to deprotect. I deprotect by using some source of the fluoride anion, because the silicon fluorine bond is even stronger than the silicon oxygen bond, which is saying something, because the silicon oxygen bond is pretty strong too. Just think of that beach that we all wish we were on here on this -5-degree day in late February. But anyhow, so I deprotect by throwing in some fluoride, and there you have your molecule. As I said before, the bad news is it takes 2 extra steps. So if you start looking at yield calculations, if this yield was 85%, this 90%, this addition of the aldehyde 98, and then deprotection comes in at 75%, wow, look at what it does to your overall yield. Drops all the way down to 56%, which is kind of a drag. There's a couple of other protecting groups to talk about. One is shown here. This is dihydropyran. And I just want to quickly show the mechanism for you. Basically, recall that this is tosic acid. So this is a nice strong proton donor, which I will show as just H+. So that's going to give me a specific carbocation, and it's going to be this one. Not putting the carbocation here, because this one is more stable. Remember that we have stabilization due to resonance. That makes a huge, huge difference. So, protonation of dihydropyran gives me this super electrophilic carbonyl. So, now my nucleophilic oxygen can swing on down here and give oxygen its lone pair back, giving me this guy, and this guy. Well, what do you do next? Obviously you deprotonate, We'll use our generic B for base, but we know that that could be the conjugate base of tosic acid, it could be the lone pairs on the dihydropyran, it could be the lone pairs on the carbonyl, it could be the lone pairs on the oxygen. No shortage of bases here. And that basically takes us to our product. Well, if you look at this, what is this? Huh, I'll be darned. This is basically an acetal. So this is just another way to make a protecting group, another way to make an acetal. And if I want to deprotect, then, well, you know what you'd do. You'd add lots of water and some acid to get the deprotected alcohol. Of course, that would be done after you've done whatever chemistry it is you want to do on the aldehyde. Probably something like adding a Grignard reagent followed by workup to give you this guy. Which of course you couldn't do in the presence of another alcohol. Alright, and the last protecting group would be the diol. So not just one alcohol, but two. How do those get protected? Well, this will look familiar as well, I am sure. So we've got a nucleophile. Got lots of nucleophiles. And electrophiles, and eventually this nucleophile will be protonated to give that super electrophilic acetone molecule, which can react with my diol and upon reaction with that diol, well, you know the rest. This is all acetal and ketal formation chemistry. Basically what we're saying is these guys are obviously these guys, and this is this. So notice that this is your carbonyl carbon. It's at the same oxidation state as this guy right here. -2 + 2, -2 + 2. Here is my acetone molecule. So there you go. That is a big exposure to protecting groups, and we will apply the use of protecting groups in some syntheses in class. In the meantime, I don't want to overdose you guys on bad jokes, but I did find a little treasure trove of bad jokes. So like, why do chemists like nitrates so much? Because they're cheaper than day rates. Okay, that's enough of that. See you in class.